Hello and welcome to another instalment of Special Relativity. Today is going to be a fun class. They're all fun, but this one particularly so. We'll learn that force isn't a tensor. We'll learn that the concept of force is relative. We'll demonstrate that force is certainly not a tensor. We'll tensorialize the idea of force, the so-called force. We'll then move from particles to fields, classical fields. We'll introduce the scalar and vector potentials for classical electrodynamics. Lastly, we'll demonstrate the so-called Lorentz covariance of classical electrodynamics. What we mean by this, not in the sense of a covariant tensor, but rather that the classical electromagnetism equations, the Maxwell equations, are unchanged under a Lorentz transformation. So the Maxwell equations can be expressed in tensor form without modification. The point being that since you can express the Maxwell equations without modification in tensor form, they need no modification in light of the relativity principle. And so this is what is meant by the Lorentz covariance of classical electrodynamics. Let's move on to 3 force and 4 force. You take an object, some material object, mass, rest mass m, let's say, apply a force to it. Question, is force relative? And the answer is yes, it is. Force is a frame-dependent concept. Ultimately, we want to tensorialize the idea of force, so we can introduce a so-called 4 force. Yep, this is a rank 1 contravariant tensor, rank 1 contravariant tensor, which tensorializes the idea of force. By definition, it's going to be the proper time rate of change, so d by d tau, the proper time rate of change of the 4 momentum. And I'll remind you that the 4 momentum, capital P, can also be written as the rest mass times the 4 velocity. So 4 momentum is rest mass times 4 velocity. The derivative of tensors in flat space-time is a tensor. F is a tensor because it's the derivative of a tensor. 4 force. Now this is a definition of the 4 force, but it begs the natural question, how is a 4 force related, which is a tensor, related to little f, the force, in a given frame, which is certainly not a tensor? So, good question. The 4 force is the proper time rate of change of the 4 momentum, as was mentioned earlier. We've learned a trick in the last class that d by d tau is the same thing as the gamma factor times d by dt. This is just moving clocks running slow by a factor of gamma. D by d tau is gamma d by dt, as we learned from the last class. 4 momentum, on the other hand, is the mass times c. This is the moving mass and the momentum. So we can now push this derivative through. Yep. So we push the derivative through. D by dt. Now m, remember that the faster a body is moving relative to u, the heavier it is. So m is certainly not going to be independent of time in general. The first term I want to differentiate with respect to t. So we have c dm dt here when we bring the d by dt in. On the other hand, p, time rate of change of momentum, is the force. So you can take this non-tensor, which is the force. You take this non-tensor, which is the force. M is also a non-tensor. It doesn't transform as a tensor either. So what I'm marking with arrows are all non-tensors. But when you put them into this 4-component object, this rank 1 contravariant Lorentz tensor, you get a tensor, which is the 4 force. If I want to proceed a little further with this expression, just for the hell of it, I'd have gamma c, instead of dm dt, I'll just write m with a dot on top. Sorry, I regret this. I'll take that back. Make that goat sound. So we have c d by dt of m, but what I could do is multiply by, pull this c in, multiply by c, and divide by c. Yep. And I've done that to make this the energy of the particle. Yep. So we have an alternative expression, albeit equivalent, for the 4 force, which is gamma into c to the minus 1, d by dt of E, which I write as E dot, and then the force. E dot, by the way, is the rate at which energy is being transferred to the point particle as it moves through space and time on its world line. So it's the power and the force, both non-tensors. Gamma's a non-tensor, but can be put together to build the tensor. And again, one of the key things about relativity is if you ultimately want to express all your physical laws in tensorial form, then you better have the quantities themselves being tensors. So we're taking non-tensor quantities and progressively tensorializing them. Tensor is a tensor if it transforms as a tensor. We know how F will transform. It'll transform in the archetypal way. So this 4 force might have components primed in the S prime and unprimed in the unprimed frames respectively. You've met these mu's before. This is how the 4 force will transform. These are the partial derivatives of the new coordinates with respect to the old. The constant coefficients of which you can directly read off from the Lorentz transformations as we did in the last class. So you can work out how the 4 force transforms. And when you work out how the 4 force transforms, you'll be able to work out how the individual components of the force transform. And this is not a tensor. It does not transform as a tensor, but the individual components of the force are frame dependent. And using this logic, transforming capital F, pulling out the bits that are the Cartesian components of little f, you can work out the non-tensor transformation law for little f. Little f is frame dependent, force is not invariant amongst frames. Now the core business of today's lecture is to move to chapter 9 where we consider relativistic fields, an archetypal relativistic field, an archetypal relativistic classical field, which is classical electrodynamics. So here I want to consider the so-called scalar and vector potentials, which I'm going to denote by phi and A. Classical scalar and vector potentials for classical electrodynamics, which I'll just abbreviate as classical EB. So this room is filled with electromagnetic field, with classical electromagnetic field, and we could choose to describe the electromagnetic disturbance filling this room in a given frame of reference via the electric field vector E and the magnetic field vector B at each point in space, at each instant of time. And this is how we can quantify the disturbance that fills space. And these are both vector functions of position and time. What we're going to do here is to give an alternative way of describing this disturbance. And instead of the electromagnetic field vectors, we're instead going to have what are called potentials. Scalar potential, phi, vector potential A. Scalar potential is a scalar function of position and time. Vector potential is a vector function of position and time. This is going to be a way of recasting the Maxwell equations of classical electrodynamics, ultimately in a way that brings their tensor form to, renders their tensor form manifest. We want to recast classical electrodynamics, instead of written in terms of fields, to write it instead in terms of potentials. Now our starting point for all this is going to be the Maxwell equations. And I'm leaving off functional dependence. Divergence of electric field considered as a function of position and time. Rho is the charge density, the charge per unit volume, considered as a function of position and time. First Maxwell equation, which is called equation 163A in the notes. Curl of magnetic field minus 1 on the speed of light. Time derivative, and I'm writing time derivative as del subscript t of electric field equals 4 pi c to the minus 1, and current density. This is a current, the charge current, the current per unit volume, the current density, 163b. Now this first two of the 4 Maxwell equations are called the inhomogeneous Maxwell equations, and they're called the inhomogeneous because they contain the source terms. We can view the charges, the charge as a function of the charge density, as a function of position and time. Imagine electrons smeared through space. We can view the charges and the currents, the flowing charges, as sources of the electromagnetic field. From a mathematical perspective, the right-hand sides aren't naught, but from a physics perspective, they're inhomogeneous because they contain source terms, charges and currents, viewed as the sources of the electromagnetic field. So the first two of these equations are inhomogeneous. The second two equations are called the homogeneous Maxwell equations because they contain no source terms. Curl of electric field, time derivative of magnetic field equaling naught, and the divergence of magnetic field equaling naught. By the way, I'm working in so-called Gaussian units here, not SI units. Yep. The only constants that appear in these equations are those that have fundamental physical significance. We're not having fictitious constants such as the magnetic permeability of free space. Only meaningful constants appear here, physically meaningful constants, in this case speed of light, in vacuum. Now these are the homogeneous and inhomogeneous Maxwell equations, and these, I don't like them at all. I like them because they're correct, but I don't like them because these are actually tensors, equations in disguise. We want to render manifest the tensor character of these equations, and these, the tensor form of these equations, 163a through d, is certainly not manifest from writing them like this. Yep. Einstein's relativity paper is called On the Electrodynamics of Moving Bodies, giving an emphasis on fields rather than particles, at least in the title. He would stare at these and see relativity underlying them. These are fully consistent with relativity. In fact, if you stare at them hard enough, relativity will come to you. Now, we want to recast these things in tensor form, and part of that is going to be introducing the potential concept. Yep. Now let's focus on equation 163d for a second. The divergence of a vector field equals naught. Now there's a vector identity which is the following. If C is a well-behaved, twice differentiable, single-valued function, it's got to be twice differentiable because you're differentiating it twice here. I want it to be single-valued because otherwise that'll screw with my head. I want it to be continuous, otherwise I couldn't differentiate it. Apart from those conditions, this function C, this vector function of space, if it's well-behaved, will obey this vector identity. So this tells us that if we were to write, if we look at the divergence of B being naught, if we were to write B, the magnetic field, as the curl of some vector field, here called A, if we write B as the curl of some vector field, here called A, then this will be automatically satisfied. This is good. This is tantalizing because if you were to write the magnetic field B as the curl of a vector potential, then one of your four Maxwell equations would be automatically satisfied. Yep. So this thing is going to be automatically satisfied. That's good because you've just reduced four equations down to three. We're ultimately going to compress the Maxwell equations still further. So this is equation 164 in your notes. So one of the Maxwell equations is automatically being satisfied. And we're making this transition from electric and magnetic fields to scalar and vector potentials, recasting the Maxwell equations to see what happens. Now let's look at 163c. What does it look like? What does equation 163 look like now that we have our vector potential A? Well, we have the curl of electric field. We add c to the minus 1 d by dt of B, but B is curl A, equaling naught. And I can factor out the curl. I'm assuming that this object here is sufficiently well behaved that d by dt and curl can be interchanged. I can factor out the curl to get the following. Curl's factored out. Yep. So this thing is vanishing. By the way, each term in this equation is a vector, so my right-hand side is actually a vector, the vector 0. Another vector identity, that if you were to give me the curl of the gradient of a single-valued, twice differentiable, continuous function phi, function of position, then this is true. By the way, this is not true if this is not continuous. As a trivial example, if if I was to write phi in cylindrical polar coordinates as theta, this is angle, looks harmless. Theta in cylindrical polar coordinates, it's not continuous, and this actually gives you a Dirac delta. It diverges on the axis, so be careful. This must be continuous, single-valued, twice differentiable. Things like this don't obey that and will screw you up. But the curl of the gradient of a well-behaved function is naught. So if we were to write this object here as the gradient of some scalar function phi, then if we set this up, its curl will automatically be naught, right? The third Maxwell equation will automatically be satisfied. Good, we've now got two Maxwell equations. Now, by historical convention, we put a minus sign here. Yep. We put a minus sign there. So all of this in round brackets equals minus grad phi, and I can just trivially rearrange this to get E equals minus grad phi minus c to the minus 1 dA dt. By the way, if you have electrostatics, turn off the magnetic field, turn off the vector potential, set A to naught, turn off the magnetic field, set A to naught, you get this expression, which you'll recognise from your studies of electrostatics. The electric field is a negative gradient of the potential. So with the pair of boxed equations, we've achieved what we wanted to. We've recast our Maxwell equations in terms of scalar and vector potentials, and something very nice has happened. Our two homogeneous Maxwell equations are automatically satisfied. We just need to worry about what happens with the inhomogeneous Maxwell equations. We're trying to simplify our life, but we're going to get this beautiful payoff where we see that these objects are in fact tensors. The natural next question to ask is, what do our first two Maxwell equations, our inhomogeneous Maxwell equations, look like when written in terms of potentials rather than fields? So let's take the first one. The divergence of the electric field is the charge density, but the electric field is given by this box, and that equals 4 pi times the charge density. Let me just multiply through by -1. Grad dot grad phi is the Laplacian of times -1 is Laplacian of phi. This negative has gone because I've multiplied through by -1. I want to interchange the d by dt and the divergence, again assuming our function to be sufficiently well behaved. So the d by dt comes first, the divergence second. I've multiplied through by -1, hence this negative sign. Fair enough, this is our first Maxwell equation, and I want to just put this to one side for the moment. If we now look at our second Maxwell equation, curl of magnetic field, but B is curl A, so this is our first term, minus c to the minus 1 d by dt of E, but E is minus grad phi minus c to the minus 1 dA dt. Because this is not looking good, right? Two of our equations automatically satisfied, but our other pair of equations is starting to look a bit ugly, but we'll see what we can do. Right-hand side of second Maxwell equation, 4 pi on c times the current density. Now there's a vector identity I'm about to use, that the curl of a twice differentiable, single-valued, etc. Vector field is going to be the gradient of the divergence minus the Laplacian. The Laplacian acts on scalars to give scalars, it acts on vectors to give vectors. There's three components here. Each of them gets a grad squared to give the grad squared of this vector field. So with this identity, we can take our second equation, this mess here, and with a little bit of algebra, which I'll leave to you, you'll find the following. Grad squared, and this is starting to look like the D'Alembert wave equation. The D'Alembert wave equation, vector field, vector potential. I like the first bit because I see the D'Alembert wave equation. I don't like the second bit because I don't know what to do with it. So we're staring at these equations. We were happy because the second two Maxwell equations, third and fourth, automatically satisfied when working in terms of potentials rather than fields. But the first two equations are looking pretty awful. This one here and this one here. Now, at this point, something's going to come to the rescue. These potentials are not unique. Just to repeat, these potentials are not unique. So, the claim is, you give me a particular scalar and vector potential phi and A, and I'll be able to determine the corresponding electrodynamic fields using the two boxed equations in the top board. But the claim is that you can transform this pair of scalar and vector potentials to a non-trivially different pair of scalar and vector potentials. And this transformation is called a gauge transformation. It's called the gauge transformation. And this gauge transformation leads to a different set of allowed vector and scalar potentials, but they imply the same fields. So phi is becoming phi prime. Similarly for A, but the claim is that when you prime these things, sure, the functions change, but the curl's the same, and this function of phi and A is the same. They lead to the same fields. You prime the potentials, but you don't prime the fields. Now that's the claim. That's the claim. And rather than proving this claim, I'm going to leave it to you to show the following. If you take your scalar and vector potential, A and phi, and you replace them with new scalar and vector potentials, you replace both of them with A prime and phi prime. And what we're going to do is pick any, notice the arbitrariness, any continuous single-valued scalar function of position and time. And I want it to be differentiable enough times to not blow up. But this could be any function. It could be the face of Albert Einstein, slightly fuzzed out, walking through space-time. Absolutely arbitrary function. And take your old A, and to it, you add the gradient of this well-behaved but otherwise arbitrary function lambda. Again, it could be the face of Albert Einstein. Replace phi prime with phi minus c to the minus 1 times the time derivative of this arbitrary but otherwise well-behaved but otherwise arbitrary function. The claim is that with this transform, this gauge transform, the resulting electromagnetic potentials, which will certainly look non-trivially different because of the arbitrariness of lambda, the claim is that they will lead to the same fields. I'll leave that to you as an exercise. Now I'm looking at the equations I'm about to mark with a star. This one here, which is one of our Maxwell equations, and this one here. And I don't like either of them because they're complicated. But there's this freedom I can make use of. The question, can I use this freedom to make my equations look simpler? Can I gauge transform to make my equations look simpler? In particular, I don't like this term. I don't like it because if it wasn't there, I'd just have a straight wave equation. In fact, I've got three wave equations, one for each component of A. I don't like this term. Question, can I get rid of it? I don't want it to be there. Can I get rid of it? In general, this will not be true. But can I make a gauge transformation? Can I choose a particular gauge transform function, lambda, to make this true? And the answer is yes, I can. And I'll leave this to you as an exercise. The point is that you can transform to primed A and phi, which will make this true. So there's actually no loss of generality in assuming that this term is naught. It just means that we've made a particular gauge transformation. There's actually infinitely many that you could make to make this term vanish. This, by the way, is called, this is a subsidiary condition. which we can make use of our gauge freedom to make our equations more elegant, more physically transparent. This subsidiary condition is called the Lorentz condition. So we have our Lorentz condition. We're trying to write all our Maxwell equations in terms of scalar and vector potentials. We only need to worry about two equations, the first two. The other two are automatically satisfied. I didn't like this term, so it's gone. And I can do that via gauge freedom. So what does this equation become? It becomes a D'Alembert wave equation. Yep. Just judging how much space to leave. The start equation of... Just lost the plot. This is becoming a D'Alembert wave equation. D'Alembert operator A and minus 4 pi c to the minus 1 j. D'Alembert operator. Vector potential. Current density. 3 scalar equations, 1 vector equation. 1/2, or 1 part of the result that we're working towards. Now, I remember this. I could throw one of these terms to the right-hand side, which says that the divergence of A is a negative c to the minus 1 of d phi dt. That's going to help me with this equation here. Instead of the divergence of A, I'm going to rub that out. I'm rubbing out this divergence of A. Why? Because I can replace it with minus c to the minus 1 d phi dt. I can replace it with minus c to the minus 1, which turns the minus 1 to a minus 2, d by dt, which turns d by dt to a squared phi. And now this equation is a D'Alembert equation, right? This is precisely the form of a D'Alembert equation, which is what we have here. Yep. Laplacian of phi minus c to the minus 2 d squared by dt squared phi equals minus 4 pi times the charge density. So these equations are actually all mathematically identical. Again, it's 4 scalar equations, all of which are nothing more or less than the D'Alembert wave equation. Same form as the wave equation on a string. So we've made use of our gauge freedom to impose the Lorentz condition and obtain a series of 4 scalar equations, all of which are mathematically identical in form, and all of which are decoupled. Each of these 4 equations, 1, 2, 3, 4, are decoupled from one another. So the Maxwell equations are starting to look a whole lot simpler when written in terms of scalar and vector potentials and assuming the Lorentz condition. But they're going to look simpler still once we write our Maxwell equations in tensor form. So in section 32, we want to demonstrate the tensor nature of the Maxwell equations. There's a certain irony here. We spoke of the null result of the Michelson-Morley experiment as giving powerful evidence for bringing relativity in. But if you do the Michelson-Morley experiment properly, you analyse it properly with the Maxwell equations, the null result falls out automatically, right? So the Maxwell equations, which is how you treat electromagnetic radiation properly, for example, in the context of Michelson-Morley, you do Maxwell electrodynamics for Michelson-Morley and the null result pops out. The key point being that the equations of electrodynamics, which would now boil down to this, plus the Lorentz condition, can be written in tensor form. Writing the Maxwell equations in tensor form is what we want to do now. Now, I'm going to be jumping around a lot on this panel of 3 blackboards, but ultimately we'll walk towards tensorially simple equations. So let's consider a charge, and that charge is going to be charge Q, moving with some velocity v through some region of space where there's both electric and magnetic fields to push it around. So the force on that particle, which will be the time rate of change of momentum of that particle, will be there'll be an electric force, which is the charge times the force per unit charge, and the force per unit charge is the field. And then we'll have another contribution due to magnetism, the V cross B term. Again, I'm working in Gaussian units, but the point is we have a V cross B term here, also proportional to the charge. Electric force, Lorentz force. And I want to tensorialize this equation, I want to tensorialize the Maxwell equations, I want to tensorialize these things, and I want to tensorialize the Lorentz condition in 20 minutes relative to our frame. Let's see how we go. D by dt, as we know, is the same, dp by dt, I could write as d tau by dt times d by dt, so chain rule, yep, acting on the momentum of this point particle. And the right-hand side I'll leave as is. Now moving clocks run slow by a factor of gamma. dt by d tau is gamma. D tau by dt, on the other hand, is 1 on gamma. Yep, that's 1 on gamma. D by dt of momentum equals, and then we have our right-hand side. What I want to do now is just to bring the gamma through. I'm multiplying both sides by gamma. So dp by dt. I've multiplied through by the gamma. I'm also going to, for reasons that will become clear soon, pull out a 1 on c. So our gammas come in to give a gamma c, e, the gamma c because of this thing, and similarly a gamma v. You know, we're trying to peer towards and see some tensors here, and we're getting there slowly.
Is that supposed to be dp by d tau?
The question is this meant to be dp by d? Is this meant to be dp by d tau?
I think that's supposed to be d tau by d.
Yes, I screwed up. Yeah, so thank you. This is d tau by dt, and this is a d tau. Yep. So you're left with a dt on the bottom, which is what we started with. Thank you. So d tau by dt becomes 1 on gamma. This is d by d tau. This is dt by d tau. This is dt by d tau. Is that what you're saying? Yep. Thanks for picking that up. I appreciate it. So we're trying to see tensors here. Again, it's ugly because we're working backwards, but you know, you're the first person to work out this stuff, then you need to work backwards. Now remember the fall velocity of a material particle. It was the gamma factor as a function of the speed of that particle into c times the velocity of that particle. So if I just drop the functional dependence of gamma on u, it's gamma c, gamma little u. Excellent. Well, here's a gamma c and here's a gamma times the velocity. So I could give this a name. I could call this U0, capital U0, and this is U1, U2, U3, which I'll write as capital U with a vector on top, indicating the spatial parts of the fall velocity. So we can already see bits of tensors appearing here. Little p is not a tensor. I'm happy that I have proper time there. There's Q, there's C. But instead of gamma c, I've got a bit of a tensor. I've got the temporal component of the fall velocity of the particle. I still have this electric field, which is certainly not a tensor, or piece thereof, at least not that I know of. This is the capital U vector that I mentioned earlier, a piece of the fall velocity tensor crossed with B, and I don't yet know how to tensorialize B. So we're trying to tensorialize the equation bit by bit. So this is equation 176 in the notes. So the left-hand side of this is the time rate of change of momentum. But remember that momentum can be tensorialized. Rest mass times fall velocity, which is the same as mc comma p, which I also wrote as mc squared on c, which is E on c, p. So part of this equation involves a proper time rate of change of this piece of the energy momentum tensor, full momentum. And since we have the proper time rate of change of this piece of the tensor, it's natural to ask the question, what is the proper rate of change of the other piece of the tensor? What is, I call this P naught, P superscript naught. So what is d by d tau of P superscript naught? Well, it's d by d tau of mc, or d by d tau of E on C. D by d tau of E on C, and then using the previous trickery, d by d tau is gamma d by dt. So d by d tau is gamma d by dt, yep, of the energy. And we still have our 1 on C there. So we have this expression for dp naught d tau. Now I want to pursue this a bit further. This is the rate at which energy is being transferred to this particle, this charged particle as it moves through an electromagnetic field. And the rate at which power is being transferred to it is going to be the force dotted with the velocity. It's going to be the force dotted with the velocity. Now the electric force will be charge times force per unit charge, QE, dotted with the velocity. There's also a magnetic force, but the magnetic force does no work because it's always perpendicular to the velocity. And again, we can recognise in gamma V a component of the forward velocity of the particle, which I'm calling here capital U vector, dotted with E. So we've got a couple of equations here, 176 in the notes and also 178, which partially involve tensor quantities, but are not yet in a fully tensorial form. Now I want to put these to one side for a moment with the promise that we will tensorialise them soon enough. We will tensorialise them soon enough. I want to change tack by saying that the time derivative of the charge density plus the divergence of the current density, this is the so-called continuity equation. It expresses the fact that in order for charge to move from one point in space to move to another, it must do so by moving through some continuous trajectory. Charge just doesn't disappear here and reappear somewhere else. That's embodied in this continuity equation. You've seen this in more elementary courses, and so I won't go through it here, but you can apply the Gauss divergence theorem to this over some arbitrary closed volume to write the integral form of this to make the interpretation more explicit. It's a continuity equation that expresses continuity. Now we have four velocity, right? And that's for one point particle. Now let's fill the room with smeared out electrons just moving around in space like boiling water. At each point in space, you'll have a point particle, the little electron or element thereof, moving in a particular direction with a particular velocity. It's forward velocity. So when you fill the room with a fluid, the forward velocity is now going to be a function of position and time. That's this object here. When you fill the room with moving charges, which act as sources for electromagnetic field, the charge density and the currents, you have this smeared out charge flowing, charge density J. I want to tensorialise this object. Yep. I want to tensorialise this equation. The claim is that if I take my forward velocity, and then at each point in space I'll have a little moving element of charge, the little blob of electrons, here let's say, moving, but at every instant of time, at every point in space, we have this moving blob of charge, which is just one element of a fully smeared out charge hooning away. If I was to go to the instantaneous rest frame of this object, it would have a certain charge density, the so-called rest charge density, which I call rho naught. This will be a function of position and time. Yep. This, by construction, is a tensor. This is a tensor. The product of tensors is a tensor, which we call the forecurrent. So this forecurrent is a tensor. Question, how is the charge density, the proper charge density, related to the charge density? Well, length contraction, if here's a volume element, right? If it's moving relative to you, it's going to be squashed in one direction by an amount gamma. So my cubic volume element at rest, when moving relative to you in a particular direction, let's say away from you, will be squashed. Yep. And if it's squashed, then its charge density is going to go up. In fact, its charge density will go up by precisely the gamma factor, because you've squashed the volume by a factor of gamma. So if you take the proper charge density and then multiply by gamma, that will amplify the proper charge density to the charge density relative to the laboratory frame. And this gamma factor is going to vary with position and time. So with this, we can now tensorialize the continuity equation. And by the way, the continuity equation is implicit in the Maxwell equations, which I'll leave it to you as an exercise. You can derive the continuity equation as a consequence of the Maxwell equations. So this flow current is rho naught and times u, and rho naught is the same as rho on gamma times u. There it is. But the flow velocity, as you've met previously, is gamma c, gamma v. That's the flow velocity. The gammas are going to cancel, and what you'll get is that the flow current, this four-dimensional version of the current, is nothing more than rho c j. Excellent. This is a tensor. We can take the charge density and the current density, neither of which are tensors, and put them into this so-called flow current, or more precisely the flow current density, and that is a tensor. If I now introduce the terminology that del subscript alpha by definition is d by dx superscript alpha, this is tensor notation. Upstairs index in the denominator is a downstairs index. This is a tensor operator, it's a tensor derivative. And you can show, and I'll leave this to you, that the continuity equation, this object here, can be written in a tensor form. There's a summation convention, Einstein summation convention operative. This is the continuity equation. And the fact that the continuity equation can be written as a tensor means that the fact that the continuity equation can be written as a tensor means that it is a tensor equation. Superb. I want to introduce another object. I don't yet have the right to call it a tensor, but what I'm going to do is to create a four-component object, the temporal and spatial parts of which are just the scalar and vector potentials, these things. I've got my eye on this because I don't yet know whether this is a tensor. It is, and I'll show that soon enough, but not yet. This is going to be called the flow potential. Yep, this is the flow potential. Now, this equation here, which is written in tensor form thus, has exactly the same structure as this equation, and therefore this equation can be written in tensor form as, again, this will have the components A0, A1, A2, A3, and the tensor form of the Lorentz condition is going to be this thing with J replaced by A. So the Lorentz condition can be written in tensor form, but again, I have yet to prove that A is a tensor, and that'll come in a second. How about these D'Alembert wave equations? We're progressively tensorializing Maxwell electrodynamics. How about these wave equations? Well, rho and J were the components of this tensor, and A and phi are the components of this object that I don't yet know whether it's a tensor or not. The point is that with this introduction of this object, these equations here can be written as one tensor equation. Yep. I'm going to introduce what's called the D'Alembert operator. Grad squared is like a Laplacian in 3D, which triangle has three sides. This is like a Laplacian in 4D. By definition, it's this object. There's Einstein's summation convention operative. If you write this out explicitly, you'll get d by dx naught all squared, which I write like this, that all-important minus sign, minus the Laplacian. I could also write this as c to the minus 2 d squared by dt squared minus grad squared. The point being that with this operator, which is called the D'Alembert, after the D'Alembert wave equation, after D'Alembert, this pair of equations just becomes, and bear in mind this is all of the Maxwell equations, these are automatically satisfied. This pair under the Lorentz condition became this pair of equations, and now I'm writing it down as one wave equation. The D'Alembert acts on this object to give the full current. So that is the Maxwell equations under the Lorentz condition. It's a series of 4 uncoupled D'Alembert wave equations. D'Alembert operator acts on each component of this to give the corresponding source term. And the source terms are built up of the charges, densities, and the currents. So that's the Maxwell equations written in tensor form. But I didn't know whether this is a tensor or not. Well, this object is a tensor. Okay, it's a tensor operator, but it's a tensor. This object is a tensor. Hence, by the quotient rule of tensor analysis, A is a tensor. So I can now call this a tensor, which is the 4 potential. So good. All the Maxwell equations, when written in terms of scalar and vector potentials, can be written in this tensor form, given here. The continuity equation implicit in the Maxwell equations can be written as such. The Lorentz condition as such. And again, notice the simplicity of these equations. So we've tensorialized or rendered manifest the tensor quality of the continuity equation, the Lorentz condition, the wave equations that are satisfied by the potentials in the Lorentz gauge. We now want to demonstrate the tensor form of 2 further things: the Maxwell equations themselves, and also these Lorentz force equations. So let's do it. Components of the 4 potential are tensors. If I differentiate, and this is d by dx subscript alpha, denoted by del superscript alpha. Derivative of a tensor is a tensor in flat space time. So this is a tensor. So is this object. The difference of tensors is a tensor. So this is a tensor. We give this a name. We call it the Faraday tensor, F. It's actually a rank 2 antisymmetric tensor. And the tensorial nature of F follows from the argument I just gave. It's antisymmetric in its upper indices. If you reverse the indices, you pick up a negative sign. Now you can write this Faraday tensor, and I'll leave this as an exercise. If you write it as a 4x4 matrix, the components of this object, well, it's symmetric, antisymmetric, so there's only 6 independent components. And by the way, EX, Y, Z, BX, Y, Z, 6 components. And when you calculate this, as you will, because this involves the derivatives of the potentials, but the derivatives of the potentials, as the top board shows, lead to the fields. Question: do these derivatives of the potentials lead to the bits of the fields? And the answer is yes. Here is the X component of electric field. Again, this is all exercise for you. Y component and Z components of electric field. X component of magnetic field, Z component of magnetic field, negative Y component of magnetic field. 6 independent components, there they are. But we've tensorialized the electromagnetic field. Because this is antisymmetric, the remaining elements are determined. EX becomes minus EX, EY becomes minus EY, EZ minus EZ, etc. Minus BZ, BY, and minus Bx. So this is called the Faraday tensor. This is a tensorial description of the classical electromagnetic field. And I claim, and I'll leave to you as an exercise, to write down the following field equations. the two homogeneous Maxwell equations, inhomogeneous, sorry, can be written as follows. In fact, since I've got 0 seconds, let me just quickly make the following thing. Fields, sources. What's the simplest possible equation I could write? Well, I've got to get rid of that alpha. There you go, it's gone. I want a differential equation. So differentiate. That's it, right? Now there's some constants here, but the point is, this is actually one of the simplest equations I could possibly write down, which links sources to fields. The fact that that's the inhomogeneous Maxwell equations is remarkable. The second equation is are the following. This one's less obvious. This is an identity. It's the homogeneous Maxwell equations. If we take this term and then write down every cyclic permutation, replacing alpha with beta, beta with gamma, gamma with alpha, then alpha will become beta, beta becomes gamma, gamma becomes alpha. We write it down again. Beta becomes gamma, gamma becomes alpha, alpha becomes beta. These are the homogeneous Maxwell equations. I'll leave it to you as an exercise to show that that's the case. Having said that, I much prefer this form here. The final piece of the puzzle is that we want to take our Lorentz force equations as given on the top blackboard and the top half of the second blackboard, and we want to write those in tensor form. I'll leave this to you as an exercise. Again, the result is one of the simplest equations you could write. I'll leave it to you the only thing we need to tensorialize is the Lorentz force stuff, proper time rate of change of the form momentum, well, these are the fields, right? So show that these are the sources, the four velocities of this room full of boiling electrons. I need to get rid of this, and sorry, we need to put a field in there somewhere, right? If I put the field down, I've got two indices. I put the four velocity down, I've got one index. I want to get rid of two of them, so let's just sum over one of them. And that is the equation up to the charge. And the bigger the charge, the bigger the force. So you expect the charge to be there. This is a tensorialization of equations 176 and 178. That was a heavy lecture, but I hope you liked it. Thank you.